Welcome to video 14.1 in our first Principles of Astrophotography series. In this video we discuss the total number of photons detected by a sensor from a celestial object. This number depends on the aperture of the telescope, the exposure time, and the apparent visual magnitude of that object.
This video is based on section 14.1 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 141, visual passband. The visual passband is centered on the average visible wavelength, lambda equals 550 nanometers, and has a bandwidth of delta lambda equals 88 nanometers.
So we've talked about the red, green, and blue broadband filters. This is something different.
All right, let's start with spectral flux density, principle 142. The visual spectral flux density is the radiant flux received in the visual passband per unit area, per unit frequency.
Okay, so that's a lot of words. Radiant flux just means watts. The power received, the joules per second received in the visual passband, that's that 88 nanometer wide passband centered at 550 nanometers per unit area. So area is measured in meters squared, so per unit area would be meters to the minus 2 power. Per unit frequency is measured in hertz, so 1 over frequency is hertz to the minus 1. This is an example of the spectral flux density. It's the spectral flux density that's associated with the 0th magnitude star, one of the brightest stars in the sky. And as you can see, it's measured in watts per meter squared per frequency.
There it is.
So that's how much that 0th magnitude star, how much energy it's sending you per unit area. Now, if you've got a bigger aperture, then you're going to capture more of that power.
Principle 143, magnitude. The apparent visual magnitude of a celestial object is an inverse logarithmic measure of its brightness in our sky. The larger the magnitude, the fainter the object.
It's weird, but a 0th magnitude star is brighter than a 6th magnitude star. And the way that I remember it is 6th magnitude is right on the threshold of you being able to see it with your naked eye. And a 0th magnitude star is one of the brightest in the sky. I think Sirius, the dog star so-called, is a magnitude minus 1. So that scale keeps on, as you go further and further down, you get brighter and brighter, and once you get to 0, you just keep right on going. So I think the sun is like magnitude minus 27,
wow,
or something like that.
Good job, sun.
Yeah, it's awesome.
It's so negative.
So, but this is the mathematical relationship. The larger the magnitude, the fainter the object. In the next slide, we're going to plot the relative radiant flux, FV divided by FV naught. And I just want to quickly show you how you can get that. If you take this equation right here and you divide both sides by 2.5, by negative 2.5, then these two 2.5's will cancel, and then you take 10 raised to the power of both sides. So then you have 10 to the negative mv over 2.5 equals 10 to the log base 10. Those are two functions that undo each other. When you raise 10 to the log base 10 of anything, you get that thing back again. So that's just fv over fv naught. So that's what we're talking about here. Fv over fv naught is 10 to the minus mv over 2.5. What that says is that the relative spectral flux density, that's this thing Fv over Fv naught. If the magnitude of the star is 0, and you put a 0 in here, then 10 to the minus 0 over 2.5 is the same as 10 to the 0. And 10 to the 0 is 1. That just means that this relative magnitude is equal to 1. Then as you increase in magnitude, you're going to go down in the amount of power emitted by the star or any other object. Generally we're talking about the total magnitude of the light coming from that object. So if you're talking about the Andromeda Galaxy, right, you're going to add up the light from the whole thing and count that toward your visual magnitude. So here's an example taken from an image that we took out in Treasureton of M35, the shoe buckle cluster. And we've identified several catalog stars here. This star A has magnitude 6. That should be visible to the naked eye without any optical aid on a clear dark night. All of these, unless you're an eagle eye, are invisible to the naked eye. Their magnitudes are smaller. This star B has a visual magnitude 7.5, all the way down to C, D, E, and F has a visual magnitude of 15.5. That's just to illustrate that the dimmer the star, the higher the magnitude.
Principle 144, photons detected. The total number of visual photons detected from an object depends exponentially on its magnitude and is proportional to the exposure time t and the square of the telescope aperture t.
Okay, so you got a star sending out light in all directions, and then you have your telescope and your little eyepiece or your camera or whatever. I'm such a great artist. And the diameter of the telescope is called the aperture. The amount of light that you should be able to collect from this star had darn well better depend on the aperture of your telescope. The bigger the aperture, the more light you expect to find. And really it should depend on the area, the actual cross-sectional area of your main lens or mirror. And that area is pi times r squared, but r, the radius, is the diameter divided by 2, so the area is going to be pi times d over 2 quantity squared. Bottom line is that this area depends on the square of the diameter. If you double the diameter, you quadruple the area. That's why this number of photons detected depends on the square of the diameter. This is just a constant which we work out in our book for a typical scenario. It's not going to be perfectly 2649. It'll depend on the optical transmittance and a bunch of other parameters, but this is a rough idea. Why is it proportional to the time?
Mo time, mo photons.
That's exactly it. I couldn't have said it better. Mo time, mo photons. If you double the amount of time you're spending looking at that 20th magnitude star or whatever, you're going to capture more photons. It's going to be proportional to the time spent on the object. Yeah, well done.
Thank you.
And then, why does it depend like this? Well, because we just showed the relative spectral flux density looks like 10 to the minus mv over 2.5. The greater the magnitude, the more and more negative this exponent becomes, and the smaller the number of photons you're going to capture. I got more joy than I really should admit out of doing this example. This is taken from an image that Ren and I took on, we spent 2 hours looking at a particular part of the sky out in Treasureton, our Bortle 2 site, and we detected this 20th magnitude galaxy. Right where those yellow pointers are pointing is a galaxy of magnitude 20. So some people had asked it, that was a couple of years ago when we were doing sea-star stuff. People were saying, well, what's the dimmest star you can see with the sea-star? Well, in 2 hours, we saw 2 or 3 20th magnitude galaxies. And frankly, that's pretty cool.
Yeah.
Because Pluto is 14th magnitude, and 13.7 I think it is, and this is way, way dimmer than Pluto is. So when you talk about the magnitude limit of a telescope, that's not a calculation for astrophotography. That's for visual astronomy. So this is the galaxy that we looked at. We looked at it for 2 hours. is through the sea star. It has an aperture of 50 millimeters, which is not a very big aperture.
Not big.
And here's our number K that we derive in the book. Here's our S. You plug all these numbers in and you get 477 photons. So this little dot right here represents, over a 2-hour period, 477 little photons coming through our little sea star camera. And I don't know, it just does something to me. So that works out to be about 15, we're talking about 7,200 seconds, 477 photons. It works out to be about 1 photon every 15 seconds.
That's a super slow drip.
So it's just, we'll hit a photon, and they don't come regularly, right? They come randomly. Mm-hmm. And so you get one, and then wait around for 15 or 30 seconds. You get another photon, hits your sensor.
What's funny about this, we were probably doing 15-second exposures. So we got a photon per exposure on average.
I think it could have been 15 or 20-second exposures, 20-second exposures.
Well, we didn't do more than 30 on the sea star. Oh, no, is it 10, 20, 30?
10, 20, and 30.
So we're probably doing 20, yeah.
Yeah, we did a lot of 20s. And so that basically means for each exposure, we might have gotten 1 photon on it.
Yeah.
So, which says a lot for the hobby, to be able to say, I got 1 photon every 15 seconds. And yeah, some of the exposures probably had 2 or 3 photons in them, and some of the photons had none.
Yep.
So it's just fun thinking about those little photons. They're massless. They're pretty thankless. They don't get a lot of attention, but they...
I'm not going to feel bad for a photon.
Thanks so much for watching.
And we'll see you next time.